All right, good. So let's move forward. We have a method of finding point estimates, right? So there are two methods to find point estimate, right? First is method of moment, and the second one is maximum likelihood estimator. So we will learn these two methods in this topic, right? Method of moment is an old method that is very useful and simple to calculate. And method of maximum likelihood estimator is we take the likelihood of each PDF and find the maximum value of the MLE. Right. So let's look at one by one. The method of moment is proposed near the turn of 20th century by Carl Pearson. Right. So this is the person who created the chi-square distribution. Right, more tractable than the method of maximum likelihood, where the model has multiple parameter. Right. So it's very simple procedure to finding an estimator for one or more population parameter. This is under method of moment, right? Consists of equating the first few moment of the population to the corresponding moment of the sample, right? So based on the theorem number one, let's say k sample moment of a set of observation x1 until xn is the mean of the k power, and it's denoted as m prime k symbolically. M prime k is a moment about the origin. So m prime k is summation of x I power of k divided by n, right? So thus if a population has r parameter, the method of the method consists of solving the system of equation by mu1 k equal to m prime k, right, for the r parameter. So this is a method of moment, right? So before we go further, let we recall some value, and we already discussed on the KMT 211, I think. So let's say recall moment about right. Let's say first moment about the origin is equal to expected of x, which is equal to mu1 prime. The second moment about the origin is equal to expected of x power of 2, right? Which is equal to mu2 prime. And the third thing that we need to know is second moment about the mean, which is expected of x minus mu and square. So this is what we call as a variance, also equal to mu2. Right, this is a second moment about the mean. Right, so and we know that the variance of x is equal to expected of x squared minus expected of x and then u squared. Right. So this is what we want to recall before we further continue with the method of moment. Right. So there is a step in method of moment. There are three steps that we need to know. The first step is we need to find the k moment about the origin of the random variable x. So we need to find first moment about the origin, or the second moment about the origin, and then find the k sample moment is the average. Means we need to find the moment of the mean, right? Mu m1 m prime k right? And then the third step is we going to equate the corresponding population and sample moment and solve the desired estimator. So we need to equate these two moment, right? So are you clear with the theorem number 1 and the step of finding method of moment estimator? Can you please state in dalam chat? So again, to find method of moment estimator, to find estimator using method of moment, first we need to find uh, moment about the origin. Second is we need to find moment about the mean, and last is we're going to equate the moment about the origin and moment about the mean together and solve for the estimator. Right. So now look at example. Example number 1. So don't worry, this example I will give, this slide I will give in class material, right? You can refer back later. And then example number 1, given a random sample of size n from a uniform population with beta equal to 1, right? So uniform distribution for continuous random variable is 1 over beta minus alpha for x is between alpha and beta. So beta is a minimum value, alpha is a minimum value and beta is a maximum value, right? So use method of moment to obtain the formula for estimating parameter alpha, right? So first step is we need to find mu1 prime. So which is equal to expected of x, right? So based on our prior knowledge, we know that mean for uniform distribution is equal to alpha plus beta divided by 2, right? If you don't know this one, you need to integrate from alpha to beta. So 1x divided by beta minus alpha with respect to x. So at the end, we will get alpha plus beta divided by 2, right? And then since we know beta is equal to 1 based on the statement, right? So we're going to plug in mu1 prime is equal to alpha plus 1 divided by 2, which is equal to mu or x bar. So this is a point estimator, right, for parameter mu. And the third step is, so we're going to solve for alpha x bar. This is a second step, which is also equal to the third step, because we're going to skip step number 2 because we don't have two parameter, right? Since we only have one single parameter, we're going to start with step number 1 and step number 3, right? So x bar is equal to alpha plus 1 divided by 2, right? So which is equal to 2x bar minus 1 is equal to alpha hat. So we know that alpha hat is equal to 2x bar minus 1. So this is the estimator for lambda hat. Alright? Very simple to find estimator for using method of moment. Right. Do you have any questions so far? You can put some question, you can raise a question on chat room. If you don't have a question, then we're going to move to the example number 2. Right. Example number 2, given a random sample of size n from a gamma distribution right? So this is a PDF for gamma distribution, 1 divided by beta power alpha, gamma alpha, x alpha minus 1, exponential negative x divided by beta, and x alpha and beta should be more than 0. So now we want to solve for alpha and beta using method of moment. So remember, now we have two parameter. So example number 1, we have one parameter. Why we should put head represent estimator, right? So this is estimator for alpha. This is a point estimator, which is equal to 2x bar minus 1, right? That's why we put head, right? So to solve for two parameter in example number 2, we know this is the random sample taken from a gamma distribution, and gamma distribution we have mu is equal to x alpha beta, right? And then sigma squared is equal to alpha beta squared. So this is the mean and variance for gamma, right? There are two ways to solve estimator, to find alpha and beta estimator using method of moment. First, we're going to use a moment about the origin for gamma distribution. Another one is we can use moment generating function with expansion into power series of t. So this the second method is going to be very tedious, right? I'm going to show you the first way, the first option to solve the problem, right? So now we know that from gamma distribution, mu1 prime is equal to beta. So, wait, before we go further, we need to look at this theorem. Theorem for gamma distribution, right? The R moment about so based on the theorem of moment about the origin for gamma distribution, right? The R moment about the origin of gamma distribution is mu prime R is equal to beta power of R gamma alpha plus R divided by gamma alpha. And we also know gamma alpha is equal to alpha minus 1 multiplied with gamma alpha minus 1. So gamma alpha plus 1 is equal to alpha gamma alpha, right? And if we want to find alpha plus gamma alpha plus 2 is equal to alpha plus 1 gamma alpha plus 1, which is equal to alpha plus 1 alpha gamma alpha, right? So this is what we learned on KMT 211, right? So now to solve the problem, based on the theorem of moment about the origin for gamma distribution, we know that if you want to find mu1 prime is equal to beta power of 1 gamma alpha plus 1 divided by gamma alpha. So which is equal to beta alpha gamma alpha divided by gamma alpha, right? So gamma alpha plus 1 is equal to alpha multiplied with gamma alpha. So this one should be equal to alpha beta. Right. If we want to find mu 2 prime is equal to beta power of 2 gamma alpha plus 2 divided by gamma alpha. So which is equal to beta power of 2. This one gamma alpha plus 2 is equal to alpha plus 1 alpha gamma alpha. So this one should be alpha plus 1 alpha gamma alpha divided by gamma alpha. So this one should be alpha right. To solve for gamma and alpha, the basic idea, we're going to plan how to solve gamma and alpha. The basic plan first is we're going to equate the first sample which is equal to mu 1 prime is equal to 1 over n summation of xi, which is equal to x bar, I equal to 1 until n. So this is the first theoretical moment. Which is equal to expected of x, right? Second step is we're going to equate the second moment about the mean, right? So remember on example number 2, we have two parameters. We're going to apply second moment about the mean. So the second moment about the mean is equal to mu 2 prime minus mu 1 prime squared, which is equal to the standard deviation. Equal to variance. So this is going to be, the sample variance is 1 over n summation of xi minus x bar squared from I equal to 1 until n. So this is what we call as a second theoretical moment a second theoretical moment about the mean, which is expected of x minus mu squared. Right. The third step that we're going to use is to continue equating sample moment about the mean, which is M2 with which is expected of x minus mu squared right? So we need to solve for the parameter. Step number 4, solve for parameter, right? So this is a 4-step that we're going to use to solve alpha and beta, right? Let me use another color. So for the first step, we're going to apply mu1 prime, which is equal to expected of x equal to alpha beta, right? So this is a mu. This is a mean for first moment about the origin, which is also equal to x bar, right? And the second step is we're going to apply second moment about the mean, which is equal to mu2 prime minus mu1 prime squared, which is equal to variance. So this one should be alpha beta squared plus alpha squared beta squared minus alpha squared beta squared is equal to alpha beta squared, right? So this is what I'm taking from the theorem for moment generating function, moment about the origin of gamma distribution. So the variance is equal to alpha beta squared. The third step is we're going to equate the first theoretical moment about the origin with the corresponding sample moment. So expected of x is equal to mu1, which is equal to alpha beta, also equal to 1 over n summation of I is equal to x bar, right? So this is a sample mean. This is the mean for gamma distribution. And the fourth step is we're going to equate the second moment about the mean with the corresponding sample moment. So variance of x is equal to mu2, which is equal to alpha beta squared. So the sample variance is 1 over n summation of xi minus x bar squared, right? And the last step is we're going to solve for the parameter, right? So let me use another color. So first step is alpha beta is equal to x bar, right? It's taken from the first moment about the origin. So alpha hat is equal to x bar divided by beta, right? For the second value, alpha beta squared, from here is equal to 1 over n summation of xi minus x bar squared, right? So alpha here is equal to x bar divided by beta. We just substitute the value of alpha into equation number 2 and multiply with beta. Beta squared. So this is going to be x bar beta, right? Also equal to 1 over n summation of xi minus x bar squared. So now to find beta hat, this one should be summation of xi minus minus x bar squared divided by n x bar. So this is the estimator for beta. So we already solved for alpha and beta. so far, do you have any question? If you don't understand, you can raise a question, or you can wait until I upload this video into YouTube, and then you can rewatch again and make sure you try to do every example I've shown to you. Right. Any questions so far? So if you don't have question, then we move to the example number 3. Right. Suppose y1 equal to 0.42, y2 is equal to 0.1, y3 is equal to 0.1, and y4 is equal to 0.23. Right. So y1 is 0.242, 0.1, 0.1, and 0.23. It's a random sample of size 4 from a probability density function, theta multiplied with y power of theta minus 1, right? Alpha hat and alpha is sama tak? Alpha hat is denoted as an estimator. Alpha just a value, right? A value of parameter. Alpha is a parameter. Alpha hat is estimator. So that is a difference between alpha and alpha hat, right? Now we move to example number 3. Suppose that we have y1 is 0.42, 0.1, 0.1, and 0.23. It's a random sample of size 4 from a probability density function, theta y power of theta minus 1, where y is between 0 and 1. So we need to find method of moment estimate for theta. So since we only have one parameter, so this is going to be very easy, right? So first step is we need to find mu1 prime. Mu1 prime is equal to 1 over n summation of xi equal to x bar. So to find mu1, so since this is a continuous random variable, right? So expected of y is equal to integration from 0 to 1. Since y is between 0 and 1, so y multiply with theta y theta minus 1 with respect to y. Right. So if you solve, if you include y into the function, it should be equal to theta y power of theta with respect to y. And this one should be equal to theta y theta minus y, theta plus 1 divided by theta plus 1 from 0 to 1. So the expected value of y should be equal to theta divided by theta plus 1. So we know that this is the second step. So expected of y is equal to 1 over n summation of y is equal to y bar is equal to mu1 prime. So mu1 prime is equal to y bar. So I just rephrase balik dia punya equation tu. Y bar is equal to theta divided by theta plus 1. So we want to make theta as a estimator. So y multiplied with theta plus 1 is equal to theta. I just move theta plus 1 over there. Theta for this case is not a variable, it's just a parameter. right? So now y bar theta plus y bar is equal to theta. So let's move uh, theta over there. Y bar is equal to theta minus y bar theta. So this is going to be theta 1 minus y bar. So this is y bar. So then theta hat should be equal to y bar divided by 1 minus y bar. So this is the parameter for estimator for theta. So we want to find point estimate. If we want to find point estimate of the theta, right, since we have the value of y, so theta hat is equal to y bar minus 1 minus y bar. So based on the example, based on the statement, y1 0.42, y2 0.1, y3 with 0.1, and y4 0.23. So y bar is equal to how much? 0.42 plus 0.1 plus 0.1 plus 0.23 divided by 4. So this one should be 0.35. So we include y bar into the formula. So 0.35 minus divide by 1 minus 0.35. So this one to be 0.54. So this is a point estimate. This is point estimator, right? So I have prepared many examples for you, right? At least we want to see all the example. So make sure you understand how to solve estimator using method of moment. So until this stage, do you have any question? If you don't have question, then we move to example number 4. So now look at example number 4. So example 4, a random sample of size n was drawn from an exponential population. So what is the PDF for exponential population? Let's say Fy is equal to 1 over theta exponential negative y over theta. So y should be more than 0. So this is a PDF for exponential distribution with the parameter theta, right? So estimate theta using method of moment. So same step, right? First step is we need to find first moment about the origin, which is equal to expected of y. So this one should be integration from 0 to infinity, y divided by theta exponential negative y over theta with respect to y. So this is going to be 1 over theta integration y expected of and exponential negative y over theta. Right. So now we have two variable here, y and exponential negative y. Right. So we need to employ integration by part. So let's say u is equal to y and dv is equal to exponential negative y over theta. So du dy is equal to 1 and v should be equal to integration exponential negative y over theta, which is equal to negative theta exponential negative y over theta. Right. and uv minus integration v du, right? So u is equal to y, and v is equal to negative theta exponential negative y over theta. From 0 to infinity, and this is going to be theta v is equal to negative theta exponential negative y over theta with respect to y. At the end, we will get theta. So I want you to solve this integration, right? So the exponential and the expected value of y should be theta, right? So this is your homework. Try to solve for expected of y. And from second step, we need to find the corresponding sample moment. So first moment about the origin is equal to expected of y is equal to y bar, which is equal to a summation of y divided by theta, right? So then we know that it's y over theta pula. This is going to be a summation of y divided by n, right? And we know that expected of y is equal to theta, right? So based on this step number 2, we know that theta hat is equal to summation of y divided by n, which is equal to y bar. So theta hat is equal to y bar. That's all. I think this is very simple, right? Now, do you have any questions so far for example number 4? If you don't have a question, then we need to move to example number 5. Example number 5 says that let x1 until xn be a random sample of size n from a distribution with a probability distribution function x power of 3, 6 lambda power of 4 exponential negative x divided by lambda, right? Find the estimator of lambda hat for the parameter lambda using the method of moment, right? So this is unknown distribution, right? If you don't really cannot recognize this distribution, you need to find the expected value of, let's say, if you want to find expected of x, you need to integrate x multiplied with x power of 3 divided by 6 lambda power of 4 exponential negative x over lambda with respect to x from 0 to infinity. So this is going to take you 4 integration by part. It's going to be very long, right? So if you can recognize this distribution, let's say we match this distribution with the gamma distribution, right? So let's say we can see the pattern of the distribution compared to gamma distribution. Let's say gamma distribution 1 divided by alpha, beta alpha, gamma alpha, x power of alpha minus 1 exponential negative x over beta, right? If you can match this one, you can see alpha power of 4, right? Let's say alpha power of 4 is this part, and 6 is equal to gamma alpha. And x alpha minus 1 is this one, right? If you can match this one. So we know that from gamma distribution, expected of x is equal to alpha beta, right? So from here, we know beta is equal to alpha lambda, and alpha is equal to 4, right? You can prove this theory by integrating the PDF multiply with x. So you can try this one. Your homework is to try to prove integration of x multiplied with the PDF is equal to alpha beta, which is equal to 4 lambda. So we know that expected of x, this is the first one. The second one, expected of x is equal to x bar, which is also equal to 1 over n summation of xi, which is also equal to 4 lambda, right? So then you can solve for the lambda hat. So 4 lambda is equal to x bar, and then lambda hat should be equal to x bar divided by 4, right? That's all. Well, if you can identify the distribution, right? You can match the distribution with the existing PDF yang kita tahu, and you can save the time of solving the finding the expected of x. Right. So far, any question? If you don't have question, then we're going to look at last example for method of moment. So let x1 until xn be a normal random variable with mean equal to mu and variance equal to sigma squared. What are the method of moment estimator of the mean mu and the variance sigma squared? So we know from here x1 until xn have a normal random variable. So to solve the parameter mu and sigma, expected of x is equal to mu, right? And this is also equal to mu1 prime, right? Which is also equal to x bar, right? Second step, we want to find the second moment about the origin. Second moment about the mean. Second moment about the mean is variance of x, which is mu2 sigma squared. The sample variance is equal to 1 over n summation of xi minus x bar squared, right? This is also equal to 1 over n summation of xi. The third step is we're going to solve for these two parameters, which is mu and sigma squared. So mu hat is equal to x bar. We already know that. And sigma squared hat is equal to 1 over n summation of xi minus x bar squared. So this is going to be very easy, right? Because we already know the expected of x and the variance of x, right? So far, we already finished the first part of finding estimator, which is method of moment. Do you have any questions so far? Any questions so far?